So, hence, I'll start by today's talk that relates to application of microwave remote sensing for the study of soil, water, ice, and snow. So, basically, yesterday I talked about the different sensors, and also I had mentioned about the applications. So, today I'll be touching upon different applications of microwave remote sensing which are applicable, where we use the passive sensors as well as active sensors. So we'll first take the study of soil. So let us see what are the parameters in land application that micro remote sensing provides. One is soil moisture estimation, then we can do crop identification and condition assessment. There is health of the crop that we can find out. The flood mapping, system mapping, geological and geomorphological mapping, forest cover, and we can identify even the forest species, what kind of forest it is. Then urban land use and land cover studies, the delineation of hydrocarbon bearing structures. So following are the parameters in land applications where we can use micro remote sensing for this purpose. And here I would like to mention again, as I talked yesterday, that various frequencies have a various uh, relationship with the various parameters. Then for the soil moisture, I had mentioned yesterday about 4 gigahertz will be the current frequency. And for biomass, about 10 gigahertz. So like this, different frequencies we use, and then we are able to find out various parameters of the land applications. So we'll see, start with the soil properties. You see, the soil they have, we start with this one, and that is the color, texture, structure, then bulk density, porosity, all these parameters, permeability and permittivity. There is most important parameter for micro remote sensing, permittivity, the most important parameter. And then the drainage, depth. So again, for each of these parameters, if we want to apply micro remote sensing, our parameter that is then in the soil texture, we want to learn about the soil texture. That means we can separate the soil using texture class. And the texture is 3 parameters. The soil will have sand, silt, and clay. This sand here, the silt and clay. I'll show you a little more detail in next slides. So now we want to find out from the soil what sort of the class it is. Using textural triangle, which I'll show you in a few minutes. And using the triangle, we are able to get really what kind of soil it is. Now, soil has 3 parts. There is a clay, then silt, and sand. And this all depends upon particle size. The larger particle size are sand, the next one is silt, and almost very small diameter particles are the clay. So here I have shown that for the sand it is about 2 millimeter to 0.05 millimeter for the sand. The silt will be 0.05 to 0.002 millimeter in the silt. Clay will be having diameters of the particles less than 0.002. So this is how the texture is defined. You will see a sand, silt, and clay. Then in sand again, you have variation, very coarse sand, then coarse sand, medium sand, fine sand, then very fine sand, then we come to silt and then clay. This again is variability with the diameters. Then the soil texture is important because depending upon this soil texture, the land use, because clay soil will have different application, silty soil will have different applications, and the sandy soil will have different applications. So this texture is very, very important for different applications. Here you see the effect of soil texture, and what you see is bedrock, and then you have this side is marine sediment. So this is how the soil texture has, the parent material has modified withering the soil forming processes to determine soil orbital texture. Then again, it's a texture class. We have 12 different classes, again depending upon the variability of the parameters. So here is a triangle which gives you this triangle is a texture triangle, and from this side is percentage clay, this is percentage silt, and this is percentage sand. And then total percentages should add up to 100. So we'll take an example. Here, what we're trying to find out that if the soil which has come to us has 42% sand, 35% silt, and 23% clay, then we take this triangle and apply this. That is 20% clay, and 43% is sand, and this one is silt is 43%. And then the point meeting is a norm. So that means we can say that this soil which is having these parameters is low soil. Then if we have these parameters, sand 32%, clay 60%, then we have this silt is 60%, sand is 10% only, and the clay is about 35%, 32%. Then this one point meeting is the silty clay. So this is soil is silty clay. So like this, using these triangles and doing this, we can find out what kind of soil it is. And then again, I'm repeating the percentage of the silt, clay, and loam. I'm repeating again: sand, silt, and clay. Please note, sand, silt, and clay. These three percentages will define the type of soil that we are having. And on that percentages will depend the kinetic constant. And on that percentages of kinetic constant will depend the soil moisture capacity. And then this can be, using macro sensors, we can detect the soil moisture, because by varying kinetic constant we get different soil moisture. So this is how we use this triangle to study the textural. And then it's a famous triangle, texture triangle, and that gives you the type of soil that we are working with. Here it is clay loam. Then soil has texture plus also various organics. And organic matter is also there, and that also helps in determining the texture or textural class. And for this one, our basically in our case, we largely depend upon the soil texture and this thing. Now soil moisture. The soil moisture helps to improve your understanding. Excuse me 1 second. So in the case of soil moisture, let us see how do we measure the soil moisture and why it is important. Please, just 1 second, sir. Please don't mind. I have some problem with laptop, so I'm just trying to take it. Now, what I'm going to tell you is that what is the meaning of measuring soil moisture? Then I'll say how do we measure the soil moisture? And this is, I'm going to tell you, is the basis of, we had a project from the Ministry of Earth Sciences. They gave us a project where we used a small satellite, and they wanted that we should find out methodology how to determine soil moisture over India using space-bound passive micro sensor and mobile phones. So we did a project for them, and then finally for 9 states we generated soil moisture maps. The methodology was taught to them. We'll come to that in a few minutes. So here what I'm talking is the soil moisture helps in improving capability of understanding and predicting the Earth's environment. That is one thing. Then it's significant focus on weather forecasting. That's very important because in the weather forecasting model, soil moisture is one parameter, and that is where we have to provide them this input. Then a new data stream on soil moisture. This is again because of climate variability and all that. So the soil moisture parameter even is required by the international community. Then recent reviews of the science program are consistently identified that the observation and characterization of soil moisture is observation priority. And in India also, the soil moisture as a parameter is used in the model for weather forecasting. Now, how do we do the measurement of the soil moisture? One is that we do gravimetric method where we bring the soil to the laboratory. Then in the oven we heat it for 24 hours at 110 degrees centigrade. So what we do when we bring the soil in from the field, we take the weight of the soil. There is a weight with a moisture inside the soil. Then we dry the soil in the oven for 24 hours at 110 degrees centigrade. They become totally dry. Then we take the weight again. Then differential weight is the weight of the water which was in the soil. And from that we find out the gravimetric, what we call gravimetric soil moisture. And then we have a time domain reflectivity, that is instrument, the neutron probe, which is soil moisture meter. And we use this one. And these methods must be calibrated against the gravimetric. And these methods give us the capacitance probe, time domain reflectivity, neutron probe. They give us volumetric soil moisture. And then you have to compare that volumetric against the gravimetric. So this is how in the field we can do both the methods. We take the sample and do gravimetric and take also that instrument that we are showing you in course. Using that instrument we do the volumetric soil moisture. And we have done that in 9 states of the country, and we generated the soil moisture maps, which will show you. Then we have other soil moisture instruments like thermal infrared technique. So we get to do soil moisture. Then of course microwave I'm talking about. Using active sensors, temperature radar we can use, and passive sensor radiometer we can use. So we get top layer 25 centimeter, and shallower than 10 centimeter could be modeling in Joule soil moisture. We can do that modeling and do up to Joule. And of course optical visibility infrared we can use these methods also. Here we are showing the slide where just here there is a microwave window in this one, and then you see here optical. The color changes due to soil moisture that all optical sensors use the information. The limitation, shallow soil penetration, and cloud contribution. If cloud is there, you will not get the soil moisture of this soil. In infrared, we do the soil temperature due to difference in soil moisture content. So these are the two parameters where we use optical and infrared. But in the microwaves, we use active sensor, use radar, and passive sensor. The advantage is that the backscattering or the microwave temperature depends upon the relative constant of the soil, which is free from atmospheric influence. And we can do better penetration depth as compared to optical sensor and day and night capability, which I told you yesterday. But the limitation here is that not only depends on the relative constant but also on the roughness and the vegetation. So that we have to separate out by different methods. Then we can get the direct soil moisture. The bare soil is there, then there is no problem. The modeling is difficult, but one is done, and we can use this for the weather forecasting. Then we have generated a model where we can get the dynamic constant if we know the texture. So by knowing the sand percentage, seed percentage, and clay percentage, then we have three constants, and this depends upon the frequency, and then we can get the dynamic constant from that frequency. That is the CD model. Okay. And of course, there is another model available, Wang and Smoggy, that also can be used for doing the same thing. So from the texture itself, we are able to get the dynamic constant. That is what is interesting here. Now, using synthetic aperture radar, how do we do that? Let us see. Now, here is the image given, the photograph taken for the where we take the soil moisture. We take the water cycle, then at time of plant sprouting, then weather and climate prediction we can do with this modeling. Understand the potential of decomposition and weathering of soil. It controls the push of the rainfall into runoff and infiltration. Especially important thing here is that high spatial, temporal, and profile variability is difficult to measure and monitor using traditional methods. And so, where there we use this radar technology for this purpose. Then here you see in the graph, this one is important. You see, this is a plant. If I'm operating a P band, 500 megahertz or 300 megahertz and all that, I can go to zone moisture activity. If I'm going with L band 42 gigahertz, I can go up to the trunk, and then sometimes I can go down, but definitely to trunk I can go. If I'm using Z band, then I only can go up to this one, and X band only on the top. So this shows that if I want to measure soil moisture, the best frequency is between P and L band, where I should choose the correct frequency. So this is when there is a vegetation. That is what is important. If there is no vegetation, in that case, you can get any of the frequencies, but to get the depth, you need either P band or L band so that you can get the moisture of the certain layer. And this one is the dielectric constant the, for the various depth scenario and for different types of soils, where the percentage of the texture is different. You get different dielectric constant. This is measured to this. Various dielectric constant is soil moisture. So we have here, you see, this was the volumetric soil moisture, and these 1, 2, 3, 4, 5 are the different type of soils, different fields. This is dielectric constant. And so the maximum dielectric constant in saturated soil around 30, between 30 32. This is the prime, and this is the loss factor. Here again, the similar graph, which will show a little more clearly. You can see here that silty clay, you have a larger, this thing, 35 dielectric constant, and the moisture content is around, volumetric moisture around 0.5 or so. Same thing here. You see at different frequencies, 1.4 gigahertz, 6 gigahertz, 18 gigahertz. 5, and this is also. Now here I would like to say that at our ICRS laboratory, we can make these measurements of the soil moisture and at different frequencies up to 40 gigahertz using the wide cell method for different textures. So we can take different texture, different soil moisture content, and then we can plot these graphs of dynamic moisture. So we will have the shown here volumetric. This is volumetric, and this is frequency wise, and this is the texture wise. So all these graphs can be plotted at the center. Then here it is shown from the surface and the angular scenario. So from 0 degree to 80 degree or 60 degree, sorry, and 20 to 40. So this is normal angle where for the rough surface, moderate rough surface, and smooth surface. So we can make a choice depending on the type of surface that we have to get the proper backscattering coefficient. Then again here you see the scattering coefficient depends upon the backscattering coefficient is canopy. So we have 1, 2, 3, 4. So you have the scattering. Please note here there is one scattering taking place from here, and then from here, and then from here. So like this, it depends upon the frequency at which we are operating, and then we can get all different types of scattering of the vegetation. That is what we and this is required. And from this one, we go for the biomass. And now we can get the biomass using this way. And here in this, you see, very interesting. Again, I'm repeating only. Response on the roughness and communication to vegetation. L band, 23 centimeter wavelength. You get the signal of the C band, you get from here 500 centimeter wavelength. X band 3 centimeter wavelength on the top. And that is which I already showed you. You see how the frequency wise you get different. And this one, polarization also has an effect on this one. So it depends upon which polarization you are using. You can use horizontal, vertical, then horizontal, vertical. So any of these four parameter polarization will give us the various informations, and then we can decide upon that which of the polarization is good for us, either we use for HH or VV or HV or VH. So here in the field, we have to go and make measurements for the soil moisture. My colleagues are in the field and they are taking reading of the soil moisture and of the crop and canopy and all those information to take from this area. Then here you see, this is very interesting. You see the noise in ASR, it depends upon the polarization and the frequency range. And this is for the C band, HH, HV, and VH. Here it is for L band, HH, HV, and VH. And here it is for X band, VV, C band, VV, and L band, VV. So from this, you can see the noise aspects in the near range, which is close to the canopy or close to the vegetation. And this one is an L band, of course, is always good as compared to C band and X band. Then the same thing, near range in ASR, where we get LVH. This is for LVH and this is LHH. The information we get. This is for L band, again HH, VH, and VV. HH, VH, and VV. These all we take and then we come to the final conclusion, which is the correct thing for us to use. That is the experimentation that we do. Then, as I told you, we did a project using SPOS, and I'll just explain to you how we did that experimentation. Now, first thing, we took 9 sites, 3 and 3, 6. Here, we are showing the 6 sites are here in this case, depending on the soil type we have taken. And that is black soil. Then this again black soil area, black soil area, black soil area, black soil area, black soil area. Yellow, I'm sorry, yellow soil. This is yellow soil. So these are the different sites we have taken. The site 6 is the yellow side. And these are all our black soil. Then so what we are trying to do in this particular first thing is that we are comparing the black soil parameters with respect to the yellow soil parameters. That's what we do in MSMR. That was in the set one. And this paper we presented. And then we did at our lab the dielectric constant measurement from 2 gigahertz to 20 gigahertz and for different percentage of moisture in the soil. And you see here there is 31%, then 15%, 23%, 8%, and dry soil. And this one is the dielectric constant variability for saturated soil 31% moisture. And you see that dielectric constant at 2 gigahertz is around 33 or 34 for saturated soil. And as we go down to the percentage, dielectric constant goes down. And for the dry soil, it is around 2 or 3. It is 2. And this is 2 or 2 to 3 for all the ranges. Whereas for soil moisture, it varies from 32 to almost 20. So this one graph is very important and that is used by us in our all analysis. I'm sorry for those, please don't mind it. My age effect. Now I'm showing you the actual experiment that we did, which was the project of the MOES, Commission of Sciences. There we had taken 9 states. You see here, starting from Assam, Rajasthan, Andhra Pradesh, Uttar Pradesh, Madhya Pradesh, Bengal, Gujarat, Kerala, and Tamil Nadu. Can you see the soils are different here? Assam has alluvial soil, Rajasthan desert sandy, Andhra Pradesh has red sandy, Uttar Pradesh alluvial, Madhya Pradesh has red and yellow, West Bengal is alluvial, Gujarat is black, Kerala is red loamy, and Tamil Nadu is red sandy. So you see the variability of this type of sand at all the 9 states. And this was told to us by IMD department. He told us the 9 states. So you see here all the there is Rajasthan, then Gujarat, then Kerala, Tamil Nadu. Then here it is this one, Andhra Pradesh, then Odisha, then this one is Madhya Pradesh, then Bengal, then Assam. So all these 9 states we took and having different variability. Now I'll show you how we did this experiment. Now what is done in this experiment? Now you see what we are doing here is first thing from ESMO satellite, which has a radiometer operating at 1.4 gigahertz, it gives us micro temperature. It is brightness temperature inputs. Now there is an algorithm by which there is inversion and we get the ESMO soil moisture from the micro temperature. And this one is given for downscaling algorithm to generate high resolution 1 kilometer maps. Then to notice. And then also this is given to retrieved soil moisture at 20 kilometer and 1 kilometer resolution. Then from here it goes to the comparison verification. So this is from the satellite. We got this range from the satellite and from the place. Now parallelly, what we do, one thing more we note here, that is that the micro temperature which is obtained here is also cross for comparison. Now what we do, we go to the field. We collect the samples as I mentioned to you. And we have the gravimetric soil moisture measured. And also we take the texture of the soil sample and find out whether this soil is sandy or silty or gloomy or whatever variety it is. Then from here you go to this model, radial transfer model or forward model. Using this model, we simulate a brightness temperature. So from soil moisture, we get the BT. The simulated BT is not here. This side we take soil moisture straight away in situ, we take it here. So now we have two comparisons here. One is the soil moisture in situ is compared with the soil moisture retrieved from SMOS. One. Second one is macro temperature, which is obtained from SMOS, and this macro temperature simulated is compared. And both comparisons are done, and then when we achieve proper range, then we say yes, now what we got is correct. So this is done at certain locations, and then once we do at those locations, we verify, we are satisfied, and at other places we don't have to do all this verification. So this is the methodology adopted for this. Now at each location, we have selected the site, and then in that site, each site we go, and then this is a 40 kilometer by 40 kilometer. Then we make out of this the focus forms 1 kilometer by 1 kilometer. And so this is in 1 kilometer by 1 kilometer. Again, we have 9 points where we have the gravimetric measurements and random points where we have the volumetric measurements. And then total we have 9 plus 15. So the minimum 15 soil moisture points are active. And then from this one, as I already mentioned to you, we try to get the total soil moisture for 1 kilometer by 1 kilometer. This is in the field we go, and we have, I'm the official here, and then we are in the field where we in Rajasthan site. Then there is another site in West Bengal where I have gone, but my colleagues have been going there. There we collect these samples. In Gujarat state where my colleagues are collecting the samples. And then in the laboratory there in Tamil Nadu, we make these gravimetric measurements and also have the volumetric measurements with the soil moisture meter. Then again, Uttar Pradesh side, then the Kerala, Madhya Pradesh, and Assam. They are different locations. My colleagues have gone and collected the samples. And this is Andhra side where all the local people also help us in this respect. Then this is the volumetric soil moisture meter, as I mentioned. My colleagues are there, and these people are trainees. They are learning how to make measurements with the volumetric soil moisture meter. Then, using this, all this data that I have already talked to you, we then generate the soil moisture maps. And for different dates, we generate. You can see now that in Rajasthan, it is to be dry during October. In October, Gujarat has a better moisture. Then here, October, Kerala, a little less. But in this case, in Tamil Nadu, we get a better scenario. Then evening pass, you get better than the morning pass. So like this, this is West Bengal, West Bengal, where we got this during October, so much of soil moisture there. So like this, we get soil moisture maps generated using the data output. And here we get water bodies based upon the soil moisture maps that we generate and get this information. Then we have trained IMD people who came to us at our center, and they were trained. And after training them, these people generated using the SSMI, the special sensor microwave media, and bodies, this microwave media. They generated these maps of Gujarat. I think that's Uttar Pradesh. And then this was Uttar Pradesh. So this way, we have completed soil moisture project and we trained IOD officials. And now today, the farmers are getting the soil moisture information from these locations from the IOD. Plus, the soil moisture is also used in the weather prediction model. These two things are applicable to soil moisture. Now we look at the water, ice, and snow. Now here, this slide itself, you see here the clouds. And here is a water. This is the water thing. This is, you can call it ice. I think that is snow. So these are the same water but in different forms. So let us see what we can do with this. Polar molecules, cohesion and addition, high specific heat, density is greater than 4 degrees centigrade, and it is a universal solvent of light. That is a group of water. Now, using this oceanographic application for micro remote sensing, we are able to measure the following parameters. Measurement of sea state. Sea state is our winds on the sea surface. Then inference of water topography in shallow seas, because to some extent we can penetrate. Then also circulation studies. Then determination of geophysical oceanographic parameters, passive microgravity, the detection and measurement of oil spills. That's very important to the oceans and ocean GI. The water has chloride, sodium, sulfate, magnesium, calcium. These are the chemicals of the water. And we see different percentages in this water. 35 grams per kg are these constituents. And we have done a project here where a simulation brightness temperature using a radiative transfer model and level of salinity from SCOS. We did a project for defense, this one, to find out the salinity of the seawater using micro sensor at SCOS. And also we collected seawater and we measured the salinity. Now we use SCOS satellite of the European agency, ERS. And then we generated models. There we found that the models which are available to us of these clean and swift and DNA models, their difficulty that they were only good enough from 30 PSU to 32 PSU. Beyond this, they were not behaving properly. So ICR has generated a new model where we could see that this new model could be working from almost 19 PSU to 50 PSU. Because at some places we get 19 PSU salinity, especially in the Bay of Bengal and also in the upper polar regions. And we get very high salinity in the Mediterranean Sea and some locations where there is a much of ocean and we get larger salinity. So this is the exercise we do for this one. And this is just a salinity map. And maximum 35.5 PSU and 23 PSU. Then, as I mentioned, our big project, and where my colleagues went to the sea and they learned how to make the feed the soil this salinity measurements, and they brought this Bay of Bengal uh, water for measurements in the water. And this was the parametric constant versus salinity that was plotted using these two models. And then, because of this difference we find here, you see that this one, they are not matching one, they are matching only up to this particular value. That side also they are not matching. They are not matching as I showed earlier. And so, this one, we generated our own model, and this is our model. It gives you even to the exact value of the salinity, which is parametric constant. So these the models are large and advanced now. Now there is a clean instance. Then for epsilon prime, double prime also, we have the similar thing. And then again we have to generate a separate model for this one also. And we also in the sea track the cyclone. The cyclone Thane was tracked by us using ESPOS and ocean satellite. And we published, presented this one in the France. In the conferences. This is very interesting that you can see that what is the category that the starting of this thing, it is tracked all the way down to the rest of the. And here is another cyclone, Neelam, that also was tracked by us. And that also the people are presented in Chennai in the conference. The universal satellite. Then we try to monitor the micro temperature of the different coastal areas. And interesting thing is that we find that the temperature, micro temperatures in the, let's say, Bay of Bengal, and when it comes to the land, they are higher, and this is the distribution of the micro temperatures of different locations that is done at 6.6 gigahertz on this side. And here it is on Arabian Sea. And I please note very carefully that here highest temperature comes out very closely near Bombay and all that. Whereas in this case, high temperature is inside as compared to this one that you see here. And then you see higher temperatures inside the Bengal where it is not in the Arabian Sea. So this is just a difference we try to study that how the micro temperature varies from this ocean surface to the land, and especially the coastal regions. That is our study. This data is from June 15, 1999, and it is for the vertical propagation and horizontal propagation. You can see here is the difference. In this case, this is the vertical propagation. This is vertical propagation. Even that also, I talked earlier, without propagation, the power will see with propagation also. That is the difference. This one. So this one again, it is the two polarizations, vertical and horizontal, in the same area. That is on the this one. You see here again, there is a difference of temperatures at up to polarizations at the same frequency, 6.6. Again, the same thing here at 6.6 gigahertz for horizontal and vertical polarization from the same location. So you can see the difference in the polarization. Then, based upon this, we can choose which polarization they should use. Then oil. We you see this is biggest problem on the larger sea, you find that these big ships, when they break or collide, and the oil spills, and because of oil spilling, the these fishes and all this marine life gets affected by that. So here in this graph, which I'm showing you here, at 34 gigahertz, there is a sort of sine wave type of thing you get, depending upon the thickness of the oil on the surface of water. At 17 gigahertz, it is over, and 5 gigahertz, the cycle is very large. So we can choose the frequency for this purpose. And 37 or 34 gigahertz gives you the best peak, because you see here the information that you get here is maximum as compared to other frequencies. So 34, 37 gigahertz will be the right frequency. We have done a study and we plotted the graph, and by weight percentage of oil, diesel, and the direct constant. So you get pure water is higher direct constant, as the quantity increases, direct constant is down. And close to pure. The same thing here also. We get from 50 to this one. That's the frequency in K band, and this is frequency in the CJ band. Around 5 or 6 gigahertz, it's around 30 to 80 gigahertz. So this again there is a difference. The lower frequency get better dynamic constant, larger dynamic constant, lower dynamic constant, higher frequency. And this one we have plotted a graph using the satellite data at 19.3 gigahertz SSMI. You see here is open region C, top of micro temperature in Bombay High. In Bombay High area, you have oil spill, whereas there is no oil spill in this area. Okay. Gives you higher temperature as compared to the. So there you can plot or you can generate the data base where oil spill is there on this type of information. Again, a similar scenario. We got Bombay High and the variable at 1.43 gigahertz. So you see the difference now. We keep track on this value in this one and in this one. You see the difference. This jump is smaller here as compared to this one. So you can use this lower frequency to get this one. At the same time, you can use a higher frequency for getting all this also. And this one shows, as I showed earlier also, that you get the larger direct constant at 37 gigahertz. This is the 36.5 gigahertz. Now, this is micro temperature. You get maximum at this one. So, if you use these frequencies, then you choose 37 gigahertz, 36 gigahertz. So one can say that 36 and 37 gigahertz are more sensitive frequencies to detect the virus when compared to other frequencies. Then also there are two instrumentation was scatter. Using this one, we will try to find out the sea surface winds. This is a 13 gigahertz scatometer, and near polar synchronous orbit. It is at 700 kilometer, 738 almost circular, inclined 98 degrees, and period is 99 minutes. Then local time passes 12 noon. And using this, we will try to get the winds on the sea surface. Then fishing zone, advisory, ocean state, forecasting, and ocean studies. These are the basic applications of this. as I mentioned, skin band spectrometer. Then using this ocean tape to the first image, this ocean image, 24 September, the ocean color photograph images of the Gujarat coast. Then also set to Maldives using ocean. Then the spectrometer. Here you get, as I mentioned already, you get wind speed from 4 meters per second to 4 meters per second. Frequency is 13.73 gigahertz. And wind speed accuracy is better than 50% RMS. And wind direction also 20 degrees less accuracy. So this way we use this spectrometer operating at 50 gigahertz to get the winds over the sea surface. This is the definition of the operational ocean surface winds over sea surface spectrometer. That on 12th October 2009. This is how we generate winds over the sea surface. You see different parts of the world. These are India, these are Neptune, these are the area of the sea surface. So at different times, we get the different winds and their directions also. Now here is our western coast, November 10, there is SAC mode, and this is the subsurface monitor using the wind vectors. Then we have this altimeter, Saral. In case of this, again, same thing, you get the altimetry of the water, inland ice sheets, rainfall, mean sea level, you will get with the help of this sea state observation, geodesic references. This is operating at 35 gigahertz, this altimeter. And it has a dual frequency radiometer also, the Saral, 23.8 gigahertz and 37 gigahertz. For the topological correction and altimeter measurements, embedded in the altimeter instrument, shared the same antenna. It is important here. Now this is how it looks like. Where you have this antenna, which is used for both altimeter as well as the radiometer. And then these are for the other application. This is the antenna. This is the nature of antenna. These are different scenario. And this is how this whole thing is the satellite Saral with Argos altimeter. Now this is the views on the being tested, and this is also being tested on the table. This is also being tested in the laboratory at ISAC satellite center. And what you see the golden cover is the golden foil, which covers the various parts of the satellite. Then we study cryosphere using mathematical sensing. In cryosphere studies, we use basically the digital elevation model. GPS also we use for this purpose. Basically, the DM based point elevation data. And it is essential to model the ice elevation change and address ice mass barriers. Then using this one, we also study the Antarctic lakes, Antarctic continent itself, many lakes, many geophysical studies of Antarctica, and development of National Antarctica Data Center for networking. So these are the things given by MOES. But if we study cryosphere, then following things we have to do for Antarctica and Arctic. And so using the satellites, we try to study, using microradiometer, we study this one. This is just a mention here, I think just for information, which all of us know, that 75% of the world's fresh water on the land is stored in the cryosphere. Then ice permanently cover 10% of the land surface, which is only a tiny fraction of lies outside the Antarctica and Greenland. Ice also covers approximately 70% of the oceans in the animal being. So these are the geographical facts that all of us know. What important thing here is that we have to know what is the health of this atmospheric scenario and what is their life. So that we use micro remote sensing for that purpose. So I'm just saying that it has a role to play in generating and mediating the conditions for a possible abrupt climate change that happens, and also is one of the factors of largest uncertainty. And these things are because of our own creation. Why this happens? Then ice caps and glaciers, important source of fresh water. That all of us know. Ice caps and glaciers. And they modulate our culture and economic evolution also. And future of sea ice is a challenging scientific problem. And especially in polar regions, is very critical and that affects various factors. And so the cryosphere provides many of the most useful indicators of long-term climate change. So if we study cryosphere, we are able to predict the weather. Then the areas that we try to study cryosphere are Antarctic region. Then we do the snow cover monitoring, then glacier inventory, then glacier retreat, then glacier mass balance, then moraine glacier lakes also we find out where are the lakes. And then snow and glacier melt runoff, then climate change studies in cryosphere. Then we have field program for establishment of chain of field observatories for collection of hydrological, meteorological, and glaciological parameters. And finally, in the last is the snow and glacier information system. So these are the things that we have to study cryosphere. Now, this is a fact of life. 10% of the world oceans are covered by the ice. Then sea influences this one. Then radiation balance, surface heat and brine fluxes, freshwater fluxes. Then using SSMI, where we have the radiometers operating at 6.8, 19 and 85 gigahertz, and at SMMR, where the scanning microradiometer, we have 6.8 and 37 gigahertz. So these frequency ranges we use to develop the retrieval algorithm for sea ice depending on ice salinity. And detection of snow layering, we use L-band interferometric data, and that will improve our knowledge of the ice sheet snow. That is very important. I think we should know this. That now having the interferometric scenario available with us, both passive as well as active, we should use this information, interferometric information, which will improve the knowledge of ice sheet snow characteristics. With L-band data, with other remote sensing data, with good knowledge of snow metamorphism, will help in understanding the snow accumulation process. So L-band data is very useful for us because of snow, ice, and this interferometry, which we are now the new technology available to us. Then emissivity difference between sea ice and the sea water. That gives us actually this how we use the radiometry for understanding the presence of sea ice. and also help in repeated measurements in terms of ice surface particles we have to investigate and develop so that we can really monitor the growth of sea ice and melting of sea ice. Now here we are showing this ice flow, biodiversity, water supplies, because they influence flood, risk, construction, transportation, agriculture. So ice and snow are important in many regions of the world. And ice and snow are important factors in global process, climate, carbon balance, and sea level. Now here are the currents, and this helps also. This is current distribute heat, thermohaline air circulation, and that depends upon the polar regions, cooling of this and warming of that into the regions. All these factors affect. Why I am showing you all this, because these are the parameters that we monitor with the help of mathematical sensing. That is nothing more. The melting of ice also depends this process, and we have to monitor the melting of ice. That we do with the help of mathematical sensing. And here it is water cycle. Again, is to an ice in the climate system. So this water cycle again depends upon the presence of snow, presence of ice, and how much, what is time factor, what is life, the duration. All these factors affect our snow, ice, and climate system. Now you see here, you see this triangle, less ice and snow. That means more sunlight absorbed by land and sea. Because of that, warmer temperatures. So this is a cycle. I start from here again, more sunlight and absorbed by land and sea, so warmer temperatures. Because of warmer temperatures, less ice and snow. And less ice and snow is because of more sunlight absorbed in this way. So this is a total. And melting of ice and snow speeds up global warming. That is what is happening here. And the brightness surface of the ice and snow covers reflect sunlight and cools the planet. But then melting of ice and snow speeds up global warming. And vice versa. So this is the factor, and that is where we have to find out. And we have to monitor constantly melting of ice and snow. And we use microwaves because I have already told yesterday the qualities of this one. We can penetrate clouds and rain. They are independent of the sun source. They are penetrating deeply into vegetation. They have the winds and height over oceans. We get etc., which I already talked. Then we have optical sensor, passive microsensors, and active microsensors. Now here again, which we just I want to repeat, differentiate between snow and its layers, see through clouds, and no special resolution. Look through clouds, high special resolution, and really difficult to interpret, but we have methods now to interpret the images. Then importance of the snow already we have talked. We'll go further. Now, the terminology that we use are snowpack, snow grains, snow density, snow water equivalent. These are the terminologies used for when we do the study of snow. Then property of snow is the insiditive, dominant factor, the surface shortwave radiation balance. The radar radiometer operating microwaves uses data. Then snow is a fundamental component of our solar energy. Snow depth is highly variable. The physical property of snow can also be quite variable. Now, using microwave sensors, we are able to get the depth of snow. And the formula used was the micro temperature at 18 gigahertz, at micro temperature at 36 gigahertz, and you can get with the A constant, which is 1.59, you are able to get the snow depth. And this, you get the radiometer data, and from this, you are able to get the snow depth. Whereas if you don't have this frequency data, Then in this case, the flow chart to find a slope cover gap using the ratioing technique. And then here is slope cover mapping, as I already told you. You can get the depth, then you can eliminate the slope cover gap. I'll go a little fast now. Then their macro emission model. Then we have slope back the brightness temperature TB, the ground temperature T0. And from there, we are able to get the down valley radiation expressed by brightness temperature T sky. Using these parameters, we are able to get, here it is, I'm showing you the layering of the snow, the layer system, wave incident from above, that this thing. And the new snow, just warming, the wet snow, the old ice crust, post grain ore, melt freeze. So these are levels of the snow, and then this is the micro temperature obtained from the bottom layer to the top layer, how it reflects. With ICRS, what we did, we tried to get the data for the Antarctica and Antarctica of the T18 and T37 gigahertz, try to get the snow depth. And also we used the data of at 10.65 gigahertz and 18 gigahertz to get the snow depth. And then we plotted. And this is how we got the variability of snow depth in the month of June 99 and December 99. And you can see the variability of the snow depth. And here in Himalayan region, we have 9 points. And then each longitude latitude. And then each of that longitude latitude, we try to do the snow depth in centimeters, variability with the date. And this we use the MSMR, MSSMI data for this purpose. So these are the variability that you see here, the snow depth. And there is a meaning in that one, which I am telling later. Now, same thing on the snow depth again, the extent of the snow and the depth of the snow in the plane, and in generally using the MSRE as a matrix supply. Then Himalayan again, the same thing, that I will talk to you. Then in this region, we try to plot the snow extent and also depth, and at 6.6 gigahertz and 18 gigahertz. You can see that difference at various times, the different snow. This is at 18 gigahertz. And this production is horizontal and vertical. And in that itself, we get difference. Here it is the vertical polarization, we get larger depth here, large depth here. And this is almost close to here. This again is almost close to here. And this is the largest depth wise. And this is the relative constant of the snow with the frequency variability. We plotted that varying relative constant with ice with frequency at different temperatures. The same thing here again. This varies emissivity, and this is angle of incidence. It varies with angle of incidence, the emissivity, and this one you see we have to take again after 80-degree density. Here it is the static coefficient, this is the emissivity. The variability of this thing, SFMR operating at 18, 21, 6 and 10 gigahertz, 10 gigahertz. Scanning multi-channel millimeter. And the special sensor, which is from 19 to 85. MSRE 6.9 to 89. SSMI again 24 channels, 21 frequencies. So these are the, why we are showing this here, because these are the data that we use for our passive macro sensors. And here you see basically the steady area, and then you see how the snow depth it is, the extent of the snow there in the environment. And again here the spread is with respect to MSMR temperature and SSMR temperature. This is how it looks like. Just want to tell you the 18 gigahertz. This is the macro temperature. This is again macro temperature. Continental condition. This again, I'm sorry, again, I have to show that again. And the depth we have got as per by this formula in two cases, 18, 37 gigahertz, and 237 gigahertz. Because of the dependent of the sensor that we have and the frequency that we have. And then this is the plot of the depth with dates from February to this one, 28 full month, how the variation is there. February, May, two different months, depth is very May, the ice is melting. And so depth is low, and February is there. So this is all that we have done studies at ICRS. Of different locations that I have shown in Himalaya. And then the typical plot of all the distinct Himalayan region. You can see that in general, you see here, this one is the larger, the maximum here, maximum is here. That shows that in the way it is melting, it is there. And that's what I want to show here. That during summer, the melting of snow takes place in this way. But the only point here I'm showing in that slide, Antarctica. This one, this South Polar region, I want to go fast about this one. This is the January and May, the sea ice boundaries at 19 gigahertz. And this is January and May at 37 gigahertz. Then here again, you see the depth of snow. And then there's 19 gigahertz and 37 gigahertz. You see the variability of depth of snow that you can see here. And I go faster. Then again, micro temperature variability and depth of snow. Then you see beyond 18 points, there is no depth at all. That we have 37 gigahertz and at 19 gigahertz. So what I did, we did a study and we looked at the freezing cycle and the melting cycle. So, 3 years the freezing cycle, 5-year melting cycle. And that cycle we took, and then we plotted the graph. You see here, from this graph, we are taking from 1980 to 2016, how the amount of snow, which was 12 into 10 raised to 6 square kilometer in 1980, has reduced to this value, which is around 10.5 into 10 raised to 6 square kilometer. Please note how the snow in Arctic sea ice has been reducing from 1980 to 2016. That is around 36 years. In 36 years, it has gone down from 12 million to 10 million. So 2 million is reduced. Now the next one we plotted, and that is the year 1980 to 2015 again, sea ice extent 3.5 to 4.5 in September month. Then here, in the month of March, from 16 to 14, again, up to 16. Then this one is plotted. You see here, from 12.5, it has come down to 9 point something in 2036. So by this time, the total Arctic ice will be melting, and then beyond that, we will have a problem with the ice. So this is so there is a decrement of this one.